Teacher,
Sorry, professor. You didn't unmute your microphone.
Hey, thanks a lot for that. Nah? How about that? So that no wonder I've been talking to myself in the last 5 minutes and nobody talks to me. Can I laugh 10 seconds? Okay, so here it is. All right, so it's time that we go back and look at B4 and B5. Now, it is one of the questions from the active session as well, how we should work on this. And my answer was something like, if you could, you should see the entire system first and try to provide the support for every beam. So if you look at the plan now, it's a bit of a trick shot, because you need to be able to see that if you are going to take care of B4 here, you have the B5 here as well. Not B5, whatever this beam is. But this beam, when you look at this beam, what would be the support of this beam? The support of this beam would be this B4, right? The beam on this edge, the brown one, cannot survive by itself. So in turn, you need to find two supports for this beam. Let's call them B0, B0. It has to be supported by something. And the only thing that can provide the support for this beam B0 is the portion of B4. So when you think that way, now you can provide two supports for this beam B0. You know that in order for this to be the support, it means that the reaction from this B0 has to sit on your B4. And not only that, now you know that your B1s will have to be supported by B4 as well, because when you look at your B1 here, this one here. I didn't mean that. Okay. This one has to be supported by B4, right? This one will have to be supported by B4. And then this one will have to be supported by B4 as well. And also this one. So when you find the two supports for all these B1s and then B0, you know that your B4 will have to carry these beams and its own self-weight. So now you can come back and take care of B4. And when you look at B4 itself, the support of B4 will come from this column, right? And when it is a column, yeah, we're done. You don't have to do anything. But B4 also needs two supports, correct? And the fact that B4 needs two support, it means that another one must come from this point. Because when somebody, if you don't look at the entire system first, some of you may be led to believe that it's B0 that provides the support for B4. But if you say B0 provides the support for B4, what provides the support for B0? B4? They cannot support each other, you know, one has to support another. So that's how it works. So when B4 needs to support B0, therefore another support for B4 has to come from this point. And that is part of B5. So you see now it's B5 that will be the final support for B4. So before you could do B5, you need to do B4 first. And B4 will support the B0 and then a series of B1s. Okay? Is there any question? So this is it. We sort of started off on this a little bit from last time. So this 3-point loads will be the reactions from B1. Okay, which is equal to 6 6,960 kilogram force. Okay, and then this brown thing is the this brown, right? We don't have brown here. That's fine. Reaction from B naught. Okay, and yeah, trickily enough, I didn't ask you to calculate the B naught, right? So in order to get this, you must DIY, right? Do it yourself. But B naught is a simple beam, which is pretty similar to B1, except that the tributary width of this B naught is only half of the typical B1, right? You see, what we've been doing here so far is not difficult at all. It's like playing simple arithmetics. You just need to know where you need to look. Okay, so it's half of that. So that means your B naught is simply the reaction here is going to be equal to half of the, I'm sorry, it's 0.8, not 0.6. 0.8 multiplied by 900, that's a total load, plus the self weight 300, so that becomes a uniform load, right? Multiply by half the length, which is 8/2. So that is our reaction, which is equal to 4080. So now you have here 4080, and then you have 6960, 6960, and then 6960. And don't forget that you also have the self weight here equal to 300 kilogram per meter as well. So now it's, you know, nothing but the analysis of this beam. Now this one is going to cost some time because it's not symmetric anymore. So we need to do some calculation. And, you know, because it's not symmetric and there's not much, we can take advantage of the situation. So I think it would probably be best if you could keep it simple. But I can't, I'm the man with a lot of tricks. So you know, let's say for B4, I'm going to call this R1. I'm going to call this R2. The R1, again, when you look at this B4, you know what I see? I see this load, this orange load is one load. And I see these green point loads, 3 of them. But if I look at the three point loads here, they are symmetric, right? And they are in span. So I know that my R1 is going to be 1/2 of that load, 6960. Do you agree? Because if I look at the green point loads alone, it's just symmetric. So that means R1 and R2 need to take half of those point loads. Correct? Can I do that? If you don't follow this, fine, you don't have to do it. But you know, for me, it's quicker. And then when I look at the this 4080, sorry, it should not be. Oh, it shouldn't be the equal sign. It should be plus. The effect of 4080 on R1 is going to be greater than the load itself, right? Because you need to take a moment at R2, or you can try to see it with the ratio. So if you look at the beam, let's say this one. I break the law into 3 conditions. But when I look at the 3080 alone, this reaction R1 would have to be greater than the load itself, right? Because you would take the moment here. Or you can, do the ratio thing that this one is greater and then that is a shorter distance. So it should give you the greater number. So this one would have to be equal to the total length, that is 8 meters, divided by this distance, which is equal to 6.4, right? So that is the effect of R1 caused by 4080. And then I can do the same with the uniform load, because the total uniform load is 300 multiplied by 8. And then if it is a uniform load, let me erase this one. It's a uniform load. This is the total uniform load, right? This is 300 multiplied by 8. And it acts at the distance 4 meters from support R2. So I can just say that this is going to be 4 over 6.4, right? Can I do that? Or if you think what I'm doing is too much, too complicated, you can just simply take moment at R2 to get R1. That's the same thing. But I don't, if you feel the structure, you don't have to take moment all the time. You can just calculate the reaction based on the ratio. Simple as that. Right? Hello? You agree with me? Is there any question? So that's how I calculate R1. It just, because you already know how to take moments, I'm just showing you another way. Okay? And then R2, we can just do the same thing. R2, it's going to contribute the same to support the 3-point load in span. So it's 1.5 load. And then this one is going, because it's pretty tricky. This one is greater than the load itself. So this one has to be minus, right? So the load is downward. And to make this equal to that itself, it is going to be equal to 2.4 over that's not true, that's 1.6, sorry. Because you need to add them up and be equal to 0, right? So it's 1.6 over 6.4, and then this is 3, 8, and 2.4 over 6.4. Okay, you don't have to do this, but for me it's quicker. And now I have reaction. This R1 is equal to 17040, and then R2 is equal to 10320. Once you get the reactions, you can get going with the shear force and bending moment diagram as well. Okay, so if I have enough space here, okay, I do. So I'm just going to try to bring it down here. I can actually do this, right? Seen some of you with the senior, does it? Okay, kind of cool, right? All right, so let's take this out. Now I got the reactions. It means that I can go ahead and perform the shear force and bending moment diagram very quickly. Now that is a point load 4080, so it's going to come down minus 4080, and now you have the uniform load of 300 per meter, so it's going to come down like this, and this is 40 minus sorry, squeeze it too tight. That spot is minus 4080 plus 300 multiplied by that 1.6. Okay, and that value is minus 4560. Oops, why did I do that? Okay, and now you face R1, so R1 is a large value, it's going to bring everything up. And this value is R1, right? So goes up to become, the ratio is bad. So I can just do that again, right? Okay. Goes up like that. Okay. And the value of the shear there, it's going to be equal to 12480. And you just proceed to do the same as the B before, but it just a little more calculation because it's not symmetric. So it comes down with the uniform load again to this point. Okay, that is going to be this number minus 1.6 multiplied by 300, right? So that's exactly 12,000. How's that? So the point load will bring this down 6960. So let me emphasize this for you. This distance is of course 6960, right? So that means that is 5040, and again the uniform load will bring this down to this value 4560, and then you realize that this time this point load is in fact greater than the shear you have here. So you see this point load will bring your shear down to the negative value for the first time, right? Are you with me? So when the shear becomes negative for the first time, you must recognize right away that here is a shear 0, but this is where your M max is going to be. So for the sake of completion, you can proceed to complete your shear force diagram. Right here is minus 2400. And here is minus 2, can't see it, 2880. And then the point load will bring this down again, right? Another point load to bring the value down to, how much is that? Minus 9840. And then you face another uniform load, and then everything will go back to 0 with this reaction. This is equal to a reaction here, which is this number. Okay. So we have completed our shear force diagram. Okay. Is there any question? Not too much, too fast for you? Oh, it's a question coming from the chat. Can you go into details about the proportion that multiply to the load again, please? Yeah, okay. With pleasure. You know, I should clear the space and try this. Okay, so let's say I have a beam. Okay, I was gonna draw the overhanging beam, and I changed my mind. Let's say I put this P here, and let's say the total length of the beam is L. All right. Now let's say this is A. This is B. And then you have R1. And then you have R2. Okay. Can you tell me which one is going to be bigger, R1 or R2?
R2.
Which one?
R2.
R2 is going to be bigger than R1? From the picture, okay, let me be clear. B is greater than A. No calculation is required. You just look at the picture and feel the structure. So if B is greater than A, it means that P is closer to R1 than R2, right? Am I right? Don't be afraid. If you're gonna be wrong, let it be this time. From the picture, B is greater than A. That means P is closer to R1 than R2, right?
Yes. Yes.
So naturally, R1 should be greater than R2, don't you think? Because the load moves closer to R1 support. So R1 should carry more than R2, right? Because the load is closer to R1. Let me continue further. I can simply say by look at this picture that R1 should be equal to B over L multiplied by P without taking the moment. Because I know from my feeling that R1 should be greater than R2. Am I right? But again, if you don't feel the structure this way yet, all you can do is just taking the moment at R2 and see for yourself. When you take the moment at R2, you're gonna get P multiplied by B minus R1 multiplied by L equal to 0. So R1 is P B over L. See that? Do you see that? So first case, let me complete this. So doing the same, I can say that R2 is A over L multiplied by P. If you don't see this, you can do the same by taking sigma moment at R1. To do that, you have P multiplied by A minus R2 multiplied by L equal to 0. And then R2 turns out to be PA over L. It's the same thing, right? But what you guys have been doing perhaps is just take the moment. Oh, you see the reaction? We take the moment. You don't try to feel what's in front of you, right? So that's the case. If let's say we have like 3 load cases in the previous beam. This is B4, right? Yeah, B4. So in B4, I can break these load cases into 3 load cases. The first one is the green point load in span, which is symmetrical. So it's very easy for me to just calculate that. So how come I write so big? Anyway, you know, the first case, this is from B4. The first case is this one. Excuse me. Okay. This is the first case, right? of a 6960. And then the second case, because they are symmetric and they are in span, so I just write it like that. The second case is this one. And then the third case is this one. Is this a uniform load? But I can look at the uniform load as a point load. But because our uniform load sort of covers the overhanging portion, so the total uniform load, WL, is acting at this distance 4.0 meter. So when I turn the uniform load into a point load, it is exactly as we have here. Right? And then for this one, it's just a little bit tricky because the load is outside. So you should feel that it's like a seesaw effect. This load will have to be big because if you look at the moment arm that multiplies the ping reaction is shorter than the moment arm that multiplies the load itself. So this ping load will have to be bigger than the load itself, and then in turn this one will have to be a downward reaction. So even with just the calculations of the reactions, you know, you don't have to take the moment like all the time. You can just feel the structure and see the equilibrium. What is required for the support to react so that everything is under equilibrium. So that's how I calculate the reaction by just look at the balance of the load. Okay, thanks a lot for asking, because I'm sure that you probably see this for the first time. It's just another way to look at the problem. Okay, is that good enough explanation? Quiet. That crystal clear, or is that completely, you know, you are completely out of the content? Yes, what? Yes, clear, or no? I think my question is kind of long, and then you have one short answer. Yes, not crystal, just clear. Are we crystal clear? Let's hope so. Okay then. All right. So now we can move back to this. Now another trick shot. Oh no, I am running out of space again. So I need to use that kind of lasso thing. So can I cut this? Ooh. Out of a boundary. Let's try again. Copy. And then paste. Okay. This is our shear force diagram for B4. Okay. I perhaps need to erase this kind of thing. Anyway, let's clean it up a little bit. Okay. So let's say if this is our shear force diagram, and move it up again. Okay. The moment diagram should be the diagram that thanks a lot for the crystal clear. Okay. Which it should be corresponding to this. Okay. So, you know, I'm just going to only do this once, just as sort of make a review for you at the same time. Okay. This is the negative area. So this one should provide the negative bending moment diagram. Okay. So you should know that this has to come down. And the value of this point would be the negative area of the shear force diagram here. Okay. So that area would give you this number. Or simple enough, this value could just come from this basic free body diagram. That point load 4080 and then the uniform load. This is the negative moment. You can take the moment of these two loads, you should get this number. Straightforward enough. And ladies and gentlemen, let me take this opportunity to underline the fact that when you have a cantilever portion like this for B4, see, this cantilever portion, this portion, or we can go back and emphasize on this portion. It's a cantilever portion of your structure. When you cut the free body diagram of this portion, you see this pink portion, your free body diagram is always this one. Well, not perfectly correct. You need to have a shear here to balance the stuff. You see, this is a free body diagram of a free end, a part of the overhanging structure. You see, when you look at this free body diagram, what you should notice is that there is nothing you can do to change the bending moment. Because it is a free end, you cut the free body diagram right before the support, you will always have this moment, then this shear. And this moment and shear will have to balance this free body diagram without any help from anywhere. So that means this moment is going to be exactly the moment caused by this uniform load and this point load, and nothing else. So whenever you have this situation, you know, moment at cantilever cannot be affected by anything else. So when you are in this situation in the real world, whenever you have the cantilever portion, there's nothing you can do to reduce the moment. Okay, if it's an in span or some short, we can always do something, try to shuffle the span, the increase, the decrease, the whatever. But when it is a cantilever, the moment is exactly what you're going to get from the load as a cantilever moment. So right here, no matter what you calculate for the in span, this number you should always get correctly. And you can, no matter what you calculate inside, this number will never change. Okay, but now if you proceed, you know that, okay, this is another negative shear area, which should give you the negative moment. But then this is the positive area. Correct? So as a result of this positive area, this area should bring your moment diagram into the positive region if you're going to have the M max. And then whatever you have here, because this is the simple support at the end. I should use a different color. Because right here at this end is a simple support. So which, you know, the moment must be 0, which means whatever this area has, it's a negative area. This area should bring the moment back down to 0. Are you still with me?
Yeah.
Okay, good. So in other words, you can choose to calculate this negative area here. Oops. The number of this negative area should give you, oh, what is this? Maximum moment, right? Instead of calculating from left to right and then try to add this number with this positive area, to get the M max. You could also calculate the M max by simply looking at the negative area on the right as well. So exactly what I did. So this M max can be calculated by using the negative area here. So, you know, if you're smart enough, you don't have to mess with the green area at all, and you calculate these two values, and then your bending moment diagram is complete. Right? That's B4, so 1.6. So that is, if you're going to calculate this area right away, M max is a negative value of a half of 2400 plus, what's that number? I can't read my handwriting anymore. 2880, right? The average of that multiplied by 1.2, which is this distance, right? 1.2, just spacing your beam. And then plus another half of, what's that? 9840 plus the reaction 10320 multiplied by another half. That will give you maximum moment right away. Okay. Any question? Okay. Hello. All right. No question. As usual. That means we are crystal clear, right? Oh, I'm running out of space. Can't believe it. So I have the B5 to contend with, another one, but it's symmetric. But B5, it's a bit, you know, it's not difficult, but why M max is negative? Yeah, I'm sorry. Yeah, I'm not really clear with that. It's a negative shear area, but because you calculate from the right, so this, right, you're right. It should be positive. The area is negative, but the M max is positive. You're right. Thank you for your comment. Okay. All right. So now let me try to go back and be fine. Let us see what happens. Okay. Now B5, we have to support B4. That number, point load here, must come from this reaction. Okay. So let's go back and look at B4 quickly again. This is the one, the pink one. This will be the load acting on B5. I have written somewhere. Where's the beam itself? Yeah, I sort of erased that, right? So that, let me say here that this one goes to B5, okay? And then B5 is a bit tricky because on the right, you have the, excuse me, on the right, you have the area of the floor only with this length. But then on the left, you have the area of the floor here. Just like B1, but it's equal to B0. So if you're not careful enough, so teach length is 1.6. Which one? You mean the tributary width on the right? Or which one? Nopodon, right? Which one are we talking about? Am I missing something? You mean M max? B4, yeah, that's why 1.6. Thank you. This should be 1.6, right? That's what you mean. Yes, 1.6. It's B4. I thought, yeah, I looked at the wrong beam. Okay, thanks a lot. So this should be 1.6, not 1.2. Okay, thank you. So yeah, common human error like this, you know, sort of makes me think that I should not publicly post my YouTube video, but it feels more natural. Okay, like this real classroom, you know. Anyway, yeah, where was I? Okay, so let's come back and look at B5. For now, you see that's the load. So the load on the blue area, you know, you add the weight of the B5 to that, because the weight of B5 should be throughout the length. And then you add a uniform load from the right on the brown area. And then you add the point load coming from the reaction of B4. So that's what you have for B5. Okay. I'm running out of space, but at least I can write B5. Okay. So what B5 is going to look like? It's going to look like this. And then you have the reaction from B4, which is equal to 10320, which is also 10320. And then you would have the, it's a blue, right? Use blue. Come on. You have this blue uniform load from the area on the left, this one, okay, that is 0.8. Sorry for, you know, moving along like this. So this blue uniform load is 0.8 multiplied by 900. That's a total floor load plus the weight of the beam, 300. Okay, and then you would have the brown uniform load coming from the right side of the floor. This is W equals 0.6 multiplied by 900. Okay. So is there any question? And again, this is symmetric. Woohoo! Right? So you should be able to finish it rather quickly after you get the reaction. Okay. So I'm not gonna show you how to calculate the reaction anymore. It's just more of the same. Let's say this reaction is equal to 15912. Now, because of the symmetric nature of the beam, we can simply draw our shear force diagram right away. That is downward. Okay. That is going down a little bit more by this, by the slope of this uniform load, which is equal to, do I have the number? That I believe is equal to 1020 kilogram force per meter. Okay, it goes down with that number. And then it meets a huge reaction. So things just go up. Now, not quite the good show for the drawing, but anyway, it should come down a little bit more. Let me try to fix that. If I go down more, I would run out of space for the bending moment diagram. So let's do that. Okay, and you forgive me for the scale. Then you have this. Now, if you really want to be completely correct, you must understand that the slope here, this slope and then this slope, they're not equal because you have two different uniform loads, right? So they're not the same. So from that again, you see that this negative area would give you the negative moment. Right there. So let me go ahead and write you the number. This, of course, must be equal to the reaction. So this is 10320, just exactly this. Point load at the end that causes the shear to drop so suddenly, right? And then this here comes down because of the uniform load. I should be minus as well. Minus 11544. And then again, this distance is equal to the reaction. Okay. And then that means right here, the shear is 4. See 4, but I say 3. So it's 4, 3, 6, and 8. That's the shear. Okay. So next step is that you know that this area will give you the negative moment here. And that is minus 13118. Okay. So the next is the moment at midspan. The moment at midspan here would be equal to this area plus that area, or you mean the orange area plus plus this blue area is the value of the moment at midspan. But you can see this is a rare case where this blue area is less than the brown area. So the brown area gives you this value already. But the blue one is so small. So that means after the calculation, you would find that your moment here at midspan is not positive at all. It's still a negative moment. Because the blue, it's about minus 7,000. 7,003, you know, okay? So this can happen. See, blue area is smaller than the brown one. Or, you know, you can simply say, if you take the moment at midspan without looking at the diagram and so, you see that the moment caused by this point load at the end is so huge, bigger than the moment caused by the reaction because of the length. And we are now coming to 11:20. I'm going to point something to you, but not now because it's going to be too much. So let me ask you if you have any question. So quiet, folks.
Can you explain about the fault on the support?
Pardon me?
Can you explain about how the fault on the support came from?
Oh, you mean this reaction? The force and support, this one?
Yes.
It's just a reaction. I didn't explain anything because I would expect you to be able to do it because the beam is symmetric. So you can just take advantage of the symmetry to calculate this reaction because it's symmetric. So this support would take this load, right? And that support will take that load. So the reaction is simply 10320 plus the shadow load. The blue one is 1020 multiplied by half the length. That is 4 meters. And then that's how much? 540? Yeah. The brown uniform load is 540 multiplied by half the length for the in span, which is 5.6/2. So that's a reaction. Simple as that. Okay. All right. Is there anything else?
I remember that in somewhere you draw the bending moment diagram as a splitted curve. Could you show me that again?
Or the moment diagram as the curve here, which
Splitted curve. Discontinuous curve.
this continuous curve. Oh, okay.
Yeah.
You probably
Maybe
mean
somewhere before the
this
first
one
grade.
for B4. Here. This two will be now this one is going to be continuous, but it's not going to be straight smooth curve. We can talk about this one because this one you have the sudden change of the shear.
I think it is the one.
I know it's not this
before.
one. I know what it is. But for this, it's not going to be as smooth as this too. But the one before this is probably this one, because yeah, it's the same reason. The slope is the same, but the smoothness of the curve is disrupted by the sudden change of the shear.
You mean the change in the slope?
Probably this one.
Change.
This one has two different slopes, but they are on the different area anyway.
So the first before this problem, it is just a notation. Am I right?
The notation or rotation?
Notation. The way that you draw the bending moment diagram as the discontinuous curve. It's just a notation for
it's not the
understandability.
notation, but you see, if I don't have the point load, it would be simply smooth continuous curve. But I draw it like this because the effect of the point load should cause this bending moment diagram not to be as smooth as what you think. Because let's say if this is a very good question. If I need more space, if I draw it like this, if I remove the uniform load, okay? If I have just the point load, what would be the bending moment diagram of this? It would be something like this. It's not a smooth one line, right? Do you agree?
Yeah.
Yeah. So this is going to be your bending moment diagram. So my point is exactly the same, but instead of having a straight line between each point load, when you add a uniform load, this becomes a curve, right? Instead. But it's not the same curve.
So the splitted point is where the change in the slope is immediate change. Am I right?
If we talk about math, this is rather difficult to explain, because when you have a curve, the slope changes all the time, right? Am I right?
Yeah.
Yeah, if you talk about calculus, good point. But everyone bear with me. So let's say if I draw this curve, the change of the slope of this curve is probably constant. Correct?
Yeah, but there's going to be a jump.
But then when you get into the second region, you now have another curve that the change of this slope is also constant, but this constant is not the same as the constant of the first curve. The rate of the change of the slope is different for these two curves. That's why I'm saying it's not a curve like when you have one uniform load. When you have something like this curve will be smooth, continuous, with the rate of change constant, because it's one equation. But this is one equation. That is another equation. So we have two equations. Yes, at this point where you know the point load is applied, the slope must be the same, because it's a continuous point. But after this point where you have the point load, the rate of change of the slope of the curve will be different. So we talk about pure math now, right?
Okay. Then I want to know that.
Let me write it down for you.
Okay.
This is like one rate of change of slope. This is another rate. Okay, two different rates of change. Okay.
Then what about the notation? I mean, to be super official in notation, do we have to draw as a splitted curve?
You mean like to draw the perfect diagrams?
Yeah, to be super official in notation.
Super official, okay.
Do we have to draw at the splitted curve?
I think if you could, it would be better for you, but it's difficult because we are drawing with the free hand, right? So I wouldn't point finger at you that, hey, you're wrong because your curves look similar. You know, it's so subjective. But yes, if you could draw a diagram like this, you would say, okay, this is one curve, that is another curve, like that. But it seems a bit superfluous at times because let's say we would be interested in this point, the value of the moment at the end of the first curve, and then the value of the moment at the end of the second curve. That would be enough, you know, super officially enough. Yes. I like the discussion, you know, and let's hope that everyone is on this wavelength as well.
Sorry, Professor.
Yes.
Could I draw the figures on your screen?
You want to draw the figure on my screen?
Yeah. I will draw.
Let you know. Let me stop the chat. Let me stop the record first.
Oh no. I can written by your screen now. Yeah. You see it, right?
What? Oh yeah. Okay. I'm.
Okay.
Okay.
And I would like to say that can it I written as this and in a curve and have some of the point that we will connect together.
You can do that because as I say, it's very difficult to try to draw two different curves, and I am not going to be like so picky saying that okay, your curves look the same, I'm gonna kill you. But the second curve then looks a little bit too ugly, if you ask me. Because it's
sorry.
It isn't gonna look like a clown like this, you know.
Yeah. I try to written in my notes.
If we are going to be super critical about this, a drawing like this is not correct. Because you now have a complete discontinuous of a curve, which is not true. The thing is that if we magnify this, if you look at this spot, the slope at this particular point must be the same, but then after this point, the change of the slope is different, not the slope. That's why we study calculus, you know.
Yeah.
And I you know, let it's gonna get personal. So let me stop the record first. It's gonna be too long anyway.